Okay, welcome everybody to my, well, maybe more regular video. I don't know, we'll see. This is a little video I'm recording on my phone, and I sort of like how they were going before, so I'll try it again. I decided to talk about the speed of light. I always found it a weird phenomenon, and then I learned a lot more about it over the years. So I thought what I've learnt and the way I understand it might help other people understand it. I used to find it very confusing how people used to describe it, although these days the YouTube is very good at doing that sort of thing. But well, my video will be out there too to help if you're having trouble. So the speed of light, we call it c, and it equals a large number, right? I don't know, it's a very large number, something like that. No, kilometers or meters per second, whatever. It's a big number per second, a big distance per second. And so you hear it's a constant for one thing. And then you also hear that it's like an upper limit. You know, that's the maximum. Nothing can be above that. Everything else has to be smaller than c. Everything. So all stuff is smaller than c. All velocities, right? And that really nothing can go faster than that. So to me, in my mind, at the time when I first heard about this stuff, it seemed to be like if we had a graph here of speed and let's say time, we're moving up in speed. You'd think that you ought to be able to sort of keep on going, right? But then no, the physicists and everybody said no, you can't. For some reason, you could do whatever you like down here, but the minute you wanted to go up here, above that spot, magically, I don't know, weirdly, why would it be not possible to keep on going? It seemed, just doesn't seem to make much sense. I mean, that's why this arbitrary number, that we just can't go faster than that. So, I'll get into it. The way I understood it, or found it easiest to get to grips with, was actually when I started learning about the history of it. Learning about the history was part of the key for me. Now, back in time, we have to go back to sort of 1880 to 1905. In that sort of time period, a lot of this discussion was happening about the speed of light. Why not before this date, you might wonder? Well, if we have, say, two people on the face of this is the Earth, right? This is not a big ball, it's actually the Earth, and these are little people, even though they're not to scale, but they're shining light at each other. Even at that, because we're talking about very, very big speeds, the time taken to get from here to there is minute amounts of time, so 0.0001 seconds, say, whatever, something very small. Now, if you've seen old clocks and stopwatches, you know, the sort of thing that looks a bit like this, and a little thing on here, little numbers all around the outside. Well, these are seconds or whatever, and if you start and stop one of these things to try and measure the speed of light, you're just going to get that it's instant. So for a long time they thought that light was basically an instantaneous thing. Around this date, though, we started to figure out ways of measuring it. We started to learn that, in fact, light... another thing, we learned that the propagation of light, its speed and what it was seemed to be a electromagnetic propagation, so an electric field and a magnetic field bouncing off each other, and you calculate how fast that would go, it appears to go at this huge speed. And then they realized that this huge speed that they were starting to be able to measure was the speed of light, and that it also seemed to be a little wave of electromagnetic stuff going through something. So this is all, some of these things are starting to come, we're able to measure this sort of speed, and we're starting to realize that it's a little wave that travels at a high speed around this sort of speed. So that's why that sort of late 19th century is starting to ask these questions about the speed of light. And having the accuracy to be able to measure it pretty accurately. Before that, just couldn't do it. Now, the first things that once you can start to measure these things accurately, you start asking in some interesting questions about the world and about stars and what can we measure. When you have starlights and you start to be able to measure that, it starts asking interesting questions about movement and speed. For one thing, we have to recall, around this time we already know that if we have the sun and we have the Earth going around the sun, then we know roughly what this distance is, and we know we go around one complete loop in 1 year. We know that the Earth is moving through space. Even back here, right? We could even probably assume that the sun is possibly moving through space too, and quite possibly that these stars are moving as well. But even just the Earth moving around the sun, we get a figure of the Earth moving through at least our local space at a pretty decent rate. I think it's 30 kilometers per second. So we're at least moving, the Earth is moving, we have starlight, and we have ways to measure the speed of light. So let's try, maybe we can figure out just how fast is the Earth moving, maybe how fast the sun is moving, how fast these other stars are moving, and we'll do that by measuring the speed of light from different stars. So they had these ways to point a telescope at a star, get the starlight, and then put it through the little new measurement devices that could measure the speed of light. And we are going to measure that this star here is one speed of light, and that star there is a different speed of light. It's at least different by this number. It's probably different by other numbers, because that star might be moving that way, and this star might be moving this way. But something started started to happen. They kept on measuring the speed of light from all these different stars. And they first thought, maybe they just fluked some bad ones, so they measured other stars. It all came out to be c. No matter which way, the speed of light was always the same number, c. So that's pretty odd, right? We haven't come across anything else that does this. If you're moving relative to something else, then the speed for different things coming, it's got to be different. So this at least should be, c plus, c minus 30, and this is c plus 30. So that's c and that's c should be at least a difference of 60 kilometers per second. And it wasn't. It was 0. This number kept on coming out to 0. So at the time, scientists had to come up with theories to explain this. One of the things I need to explain about light and other beliefs at the time is to do with a thing called the ether. Now, ether was assumed to exist for at many different times in history, and even to this day it still gets mentioned in physics papers. But at this stage, around this date, it's a much stronger thing, even though nobody quite knew what it was or how it was. It had to be there. In many ways, it was thought it had to be there because light did seem to act very much like a wave. It bounced around like waves do, and all the other waves that we'd ever known. So if this was a sound wave, then that's a sound. It's a pressure. It's a change in pressure, it's a change in pressure in something. So air or water. So the sound itself is not something. It's actually a change in something else. It's the change. So a rapid pressure change creates sound. And it's in a substance, in water or air. There are other types of waves. You had water waves, and that obviously was a change in the surface of the water. And the wave itself didn't exist outside of its movement of water. It was a way to describe the way the water moved. So it was essentially thought that a light wave, since it's a wave, must be a wave in something. There's also other reasons why an ether seemed attractive, because there were quite a few forces that were being enacted at a distance, so gravity and electromagnetic forces, and it didn't seem to make any sense that they wouldn't actually be transmitted through some sort of substance. So we had the idea of an ether at that time. And I'm drawing some ether here, right? It's a thing that permeates through all the universe, and light must sort of travel through it. So really, when we're talking about this speed of light being constant, we can maybe explain that in a few different ways. And we can at least do a few tests. If it's traveling through the ether, and we then have to make a decision about what is the Earth travelling through the ether to. So if the Earth is travelling this way, does that mean the ether relative to the Earth is going the opposite way? And since the Earth is travelling in one direction most of the time, that means the ether is travelling in a pretty constant direction the opposite way. It's not swirling around or anything. It's a constant wind, so they call it an ether wind. So they had experiments to try and test that. I'll talk about that in a second. They thought that would be interesting to test if there was an ether wind. If they couldn't detect an ether wind, then there was this other theory. The other theory was that, and this will sort of help explain why all these speeds of light are the same. If the ether actually was being dragged by the Earth, so as the Earth moves, it drags the ether around, even a little bit of ether that's just on the very surface of the Earth, into the height of our experiments in rooms and stuff. It's all being dragged along. So if we did an experiment right on the surface of the Earth, we're basically a speck on this scale. Then we ought to see, this ether drag. And if the ether was being dragged, And it didn't matter what the speed of the stars were and what their ether was doing where they were. The fact is that if the ether is being dragged along, then we ought to be able to see that the speed of light would be the same, because it's travelling through the ether, which is the same. It's the same ether. So ether drag. So we can test, maybe try and test for that. So a couple of experiments have been set up. One of them, let's go over I think there's a Michelson more, you can look it up, Michelson Mosley or something experiment. That one was looking for an ether wind, and what they decided was that if there was an ether wind, let's just call this a wind now, and we had a little a generator of light here, and this is on the surface of the Earth, and we bounced light going that way, and then off a mirror and back again, and we bounced light going this way, and then back again off a mirror, and we had a little device in the middle that measured how long it took light to go from here to there and over there, and they could sort of see by how these two light beams interfered with each other in the little device, you'd see if their time travelled would change. And why would it change? Well, it would change because they put all of this on a big rotating table, and then they would shoot the light off and they'd rotate this table slowly, and as the light beams went side on to the ether wind, and then in line with the ether wind, they would see each of these beams' lights change in time. And that would tell them, so if they had a little graph, if this is a little graph, they would see that as the difference in time would sort of gradually do this as they rotated the table around. Obviously, if it's going with and against the ether in this trip here, that's going to take longer, because the trip against the ether doesn't counteract the trip with it, and this one here would take a shorter amount of time because it's not experiencing any burden from the ether, and it's directly perpendicular to it. Yeah, I mean, it's essentially, there has to be some difference. If this ether is affecting this thing, as you turn it around, you would see these rolls of these two beams of light exchange places. So they'd see some sort of curve. That would be fine if there was an ether wind, and we'd find it there. There's another experiment, I'll leave that one there. There's another experiment for the ether drag. Now let's go to a new page for that. Now ether drag, they thought if it's just the Earth dragging stuff, the Earth is just a big heavy dense object, so we ought to be able to get a big heavy dense object in a room and create drag of our own. But we're going to do a really good job of making a big dense heavy object. And what they did is they made this thing. If it says, I'll just do a little side view. So it's got a little top bit, and it's got an axis. If you ever see these lines, it means that's an axis, like a center line. And it had a little thing there. And then I had a big base on it, glued to the ground. That's the ground down there. This is the ceiling up here. There's a little gap between these two things, and if you looked at these things from above, they were a big circle. So this was an experiment where they made huge concrete, actually I've forgotten if it's concrete or cast iron, big lumps. Anyway, they were very heavy, tons and tons of, let's call it concrete, but they might have made a metal one too, that could rotate. And they had a gap between them, conveniently, just big enough for a little beam of light that they would shot through the middle. Up through there. If you're looking from above, they probably pass it sort of along through there like that, right? So this is under the this is assuming this. So ether is everywhere. Light's traveling through it, sort of everywhere. Has to be. So it's in the room with them. It's dotted everywhere through everything, and these objects. When you spin this around, and I'll put theirs in a minute, it would spin the ether with it. So if you're spinning these things, then you're going to get some ether being dragged along, and would be happening in here too, right? It has to happen outside the effect, because on Earth we're seeing it outside the surface of the Earth, and yet we're claiming that it's the Earth dragging the ether. So if these two big things are spinning around, so we put a big spin on this thing. And sort of like that, say, we have to have ether being spun around with it. Now we can, before we start spinning though, we can have our light beam, and we can split it off. So we have one of the beams coming in there, and then another one. So we split this beam into two, and we send one through the middle there. We send another one out to here, and then we join them back up again. And a little box that measures the change. So we're much better at measuring changes in this speed than we are the actual speed. A change will show up really easily. And if we start doing the experiment with it turned off, it's not moving, then we get one result. And then if we start it spinning, we should see that result shift. And then if we, because this one's getting a push, right? Then we can turn this around and we can spin it the other way, and then the ether gets dragged the other way, and that should slow it down, so we get another shift, and it should be the opposite shift to the first time. Now, so that should mean when it's 0, we should get one answer, and we'll just call that C. And then if we're going a plus direction, we should get C plus just a little bit. And then if we're going the other way, we should get C minus a little bit. So ideally, at the end of the day, we have two little bits. Two little bits is the total difference between spinning that way and that way. And that, if it works, will show us ether drag, and that will explain the speed of light being the same from measuring all different stars. So they did this, and they got, where's a nice big red tick button? They got C was 0 at the stationary, great. They turned it on, started rotating, and they got this result, and they were all pretty happy about that. And then they thought, okay, now let's stop it, and then turn it the other way. And this is where it all went pear-shaped, because they actually got the same result again. And so it was a big fail, because that wasn't supposed to be like that. And when they looked at it and they realized that what must have been happening, you've got to remember, this is 1900. This is like way worse than your washing machine that bounces around. This is a giant heavy thing rotating on some bearings in a room, and guess what? It makes everything shake to bits. The things are all shaking. It's all shaking. Everything's shaking, and the little and that shaking made this little difference here. when they eventually came up, sort of decided that there was no measurable impact from spinning these things. Yeah. And the other experiment, when they did this one, they turned the disc around, they didn't get this nice line like that, they got a straight line. No change. No matter what you did, the light beams stayed the same. So they couldn't detect an ether, no matter what they tried. So then lots of people thinking of different other ways this could possibly be true. And Einstein wasn't the only one to be considering the other part of the equation, and there was this concept that if, where's the Earth moving? Maybe this movement itself changes something. It's quite a high speed. Maybe that changes something about how we measure length. So maybe what we call 1 meter is one thing here, but if you're going at this speed, it becomes a different thing. And they were going to use that to try and explain. You could there were ways that you could see that C might be the same if this was true. Einstein had a similar thought, and it's probably not exactly how his thought processes went, but I'm just sort of going to paraphrase a little bit. If we said that C is this number, and we're measuring C no matter what whatever it is, I can't remember. It's not lots of zeros. If we're measuring this to be true all the time, so rather than question that, the number, what if we start to question the units? Maybe these things are changing. Also, if we're going to have this as a fixed result, so let's just make that work in terms of the maths. So then we had to I guess their thinking at the time is that if you add different numbers to C, so if you have C plus some velocity, maybe that's this one, it still equals C. And if you had C minus some velocity, still equals C. So what mathematics do we need to make that true? Essentially they're saying, okay, let's say we've got V1 plus V2, and it can equal V3 as long as V3 is only ever less than C. That's a less than sign. And so they just ran with the maths. They had to recreate how you do additions in velocity, and so they became weird things. And this is not right at all, but that's like 1 minus C or something plus V2 over 1, and this is totally wrong, but I'm just making the point that it's equals V3, 1 minus C over 1 minus C squared or something, and blah, 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 blah. With this type of maths, and how you added these velocities using this maths, you could make this true. And rather than question it, they just went with it. Let's just see if this maths, what happens when we do this maths. And it turns out what happens is, it means that these things have to change. Now to explain that, because if these things are able to change, then you can always measure c to be the same number. I'll show you a little demonstration of some of the thought processes they would have had to have gone through. Now, I think they did this with trains back in the day, but let's do rockets now. We have rockets now. And it seems much more likely. So we have a rocket, and it's going very fast. For this part, we'll just some people in Windows on board, and we have a person on the ground. It's a Japanese character person, and we have a little person here, right? And let's say that this speed here is sort of 0.5 c. The rocket's travelling at 0.5 c. And let's say this person's 0, so he's not going anywhere, and we have a light beam going past the whole lot. Now, what was uncomfortable for a lot of people, but these people like Einstein just sort of went with the flow, was that when this person here measured the speed of light going past here, and this person here measured the speed of light going, they had to both measure it as c, even though this person is travelling at this speed that way. So normally you'd say that they would measure the light to be 1.5 c, and this people would measure it at 1 c. But we have decided that it can't be true because we are not measuring that. We're not seeing that on Earth. So what has to happen? Well, it turns out that this person and this person can no longer agree on what a meter is. So they say a meter is that long, and these people, if they're moving at that speed, have to say a meter is that long. It's different, right? The percent is not important right now, it's just it's a different length, it's a shorter length. The other thing that has to change is they talk about how long a second lasts. So if I was to say a second is between this dot and that dot, then for these persons still, then for here, these people will say a second is from here to here, much longer. If the person on the ground is perception, if they say a second is this long, and I'll just put a little s there for second and a little s there. So they say a meter is that long and a second is that long, and then they see this beam of light and they do a measurement of the speed because of their meters and their seconds. They say that light is going at that speed, ... And this person agrees, except their meter is that long and their second is that long, and because they're living in that world, it all works out for them too. They say, yes, this light beam is going at that speed, that many meters, at that many seconds. It did seem pretty odd that would be the case, but the maths checked out, right? This is one way. If you have a new meter and a new second for this person, that is one way that you can make it true, that you will measure c to be the same no matter what's going on. That's how that's what has to happen. Now, obviously, fast forward decades, and eventually measurements are made, and indeed, it does seem to be that for things travelling at a speed, these people do disagree. there are various experiments that show that these things do not match anymore. Now, I should just be clear, it's just a disagreement between each person. Neither of them are correct or wrong. This person in the rocket will measure this meter and swear that that is what a meter is, and that didn't change, and that they will swear a second is that length. They don't feel to them, it feels like the same second. It always feels like the same second. It's when you're observing the other person. So if this person's watching this one in the rocket, and they happen to have a clock on the wall, that clock will go slower. They'll see it going slower. Not only that, but the rocket, which started out life being on Earth, stationary that long, they don't see it to be that long. The people in there do, they still see it to be the same. But us on Earth, looking at the rocket travelling along at that speed, they will see that the rocket now appears to be a lot shorter. Even this bit is all stumpy, right? It becomes a stumpy little rocket, and the windows are no longer circles, they become ovals. They all become squashed in that direction of travel. To them, it doesn't make any difference because their meter is also squashed in that direction and they feel like it's the same rocket. But we look at it and go, no, your rocket is squashed. And again, this is something which we have seen with, especially with particle physics. So when particles are flying around, they become squashed. And also the length of time that they experience starts to change from our length of time that we experience. So, Now, it's a thing of measurement. Now, the reason I'm going to show you that it's a thing of measurement by examining one scenario in particular. This is about traveling to the stars, right? Because at some point it's hard to know whether this is. It still feels sort of unbelievable and a sort of arbitrary limit, but it really does just always come back to this need to measure C to be the same no matter what we're doing. And the key word is measure, in a way. Now, to demonstrate that, let's imagine that this squashed rocket is flying. It's flying to Alpha Centauri, and we'll start. It took off from Earth, so Earth was back here, and we'll put this person on Earth. There's a little person there on Earth now. And we will draw a nice star up here. And that one is Alpha Centauri, we'll put AC. And I'm pretty sure that's one of the closest stars, right? We'll just make some space. Get rid of this guy. So we have Alpha Centauri. I guess Alpha Centauri is approximately 4 light years away. So that distance, 4 light years, that's a distance measurement. But it tells you, if you're travelling at the speed of light, how long it will take you to get there. Well, it tells you how long we will see something getting there in. And you'll see what I mean by that in a minute. Let's just tidy that up a little bit. I'll just go LY for short. Now this rocket, we need it to travel. These effects don't really start happening until you're going really quite fast. And this will also make the maths a bit easier. Let's say it's travelling at 0.999 C. And there are calculators online, you can actually get the exact numbers. So these are not exact numbers, but you can get the idea. The principle is very close. What happens when this rocket's travelling at 0.999 towards from Earth to Alpha Centauri? Well, for the person on Earth, they see it get there in near on 4 years. Because 4 light years, this is near on speed of light. 4 years later, they see the rocket get to Alpha Centauri. Great. Except we've already talked about the fact that the seconds travelled, the seconds passed for the passengers is different to the seconds passed for the dudes back at home. So if we see them in 4 years get there, but their seconds are different. So their seconds, they don't get there in 4 years, and I'm just going to make it a convenient 48 times difference. Their time, they call this time dilation, right, is going to be a much bigger number than what you think. It's possibly at this sort of speed here, their time dilation might be 48 times. So for every 48 of our seconds, they have only one of their seconds. So what did that mean? That meant that we saw them get there in 4 years, but they felt like for them, only 1 month. 1 month had passed. 1/48th. 1/48th of 4 years is 1 month, right? So they've just done that journey to Alpha Centauri in 1 month. Now, you might think that they've violated the speed of light that's supposed to be you can't go beyond it already. How? Because from their point of view, they've just measured that they've travelled that distance in way less than 4 light years, in 4 years. So they can't have measured their speed of light to be just that. They must have measured it to be a lot different. But the thing we have to remember is the distance changed as well. So when you start travelling at that sort of high speed, and I mean high in the sense that it's very, very close to the speed of light, in a way you can start talking about a high speed being closer and closer and closer to the speed of light, and you can get infinitely close to the speed of light and sort of go infinitely fast. You're not actually ever going faster than the speed of light, but you can get places infinitely quickly, put it that way. Because as we went faster and faster, we said not only the speed, the time changed, but also their measurement of distance changed. Not only the measurement of distance in their little rocket, but the measurement of distance in the universe. So when they're travelling at this speed, Alpha Centauri is no longer 4 light years away from Earth. It's now only, and I don't know you can do a calculator and find the exact number, but for this speed, it's only one, what would it be, 1 light month away to go. Something like that. I don't know if these contract and dilate at the same rate. I've forgotten. Anyway, it's a lot shorter distance. I guess that would make sense. If they're travelling for 1 month near the speed of light, then it must be roughly 1 light month away that they've travelled. So at this speed, the distances in the universe shrink. And it's not just... so it really does draw into question about this whole what is space and distance and velocity. You really can't think of them as being linear things anymore. And so really from their point of view, they do in fact measure that distance to be a lot smaller than us. We do not agree. This person and these people do not agree on the distance between stars, which I find quite interesting. And very rarely do you see that discussed. So yes, in a sense, we can travel to the stars, and we can do it quickly. If you put another 9 on the end of there, you might get this down to 1 week or something that they'll get there. So you can get to Alpha Centauri really fast if you want to. The thing that you can't change, the thing that is irreversible, is the time passed on Earth will always remain the same. So you can go to and from here and come back again, and you can do it in very, very quick time. But a minimum of 8 years will pass on Earth during that same trip that you've done in whatever time it's taken you. So yeah, weird things happen to everybody else when you're travelling fast. They don't happen to you, but they happen to everybody else. And to everybody else, weird things happen to you, but not to them. So it's always a matter of all the weird stuff's happening to somebody else. That's why they say it's all relative. Yeah, so I don't know, does that help explain it a little bit better? It's not so much an actual limit in maybe the way you're originally thinking. It's really a limit in measurement. So you really can go very fast as you want, but you'll never be measured to go faster than c, no matter who or what you're doing to measure it. Other things change. So back on Earth here, we always measure c because our speed here relative to their speed there is mucking with our measurements, units of measure, and hence why we always measure c, and hence why if you always measure the speed of light to be the same no matter how fast you're going, it sort of says you can never go faster than the speed of light, because you can't measure it to be any different. So yeah, how can you measure it? Yeah, so that's the other part of it, and it's a constant in the sense that we never measure it to be anything else but this number, right? It's constant in that sense. There is some ideas that maybe it changes throughout the universe, or it could have been a different number, but it seems to be a matter of the way space-time and light and our perception are all mixed up, that it is a constant because it, in a way, defines what time is. Okay, let me know if that makes sense. Ask questions in the comments, or sort of 5 viewers of this, and maybe I'll do another one sometime in the future. Bye for now.